This is part 3 of the module which I call PCA for regression, and in the first two parts we discussed what is this different kind of regression compared alternative regression to OLS, and sometimes it's called type 2 regression in some fields, or orthogonal regression and so on. It has different names. But we figured that this regression uses principal component analysis and first principal component to come up with a regression line, and the interpretation of this regression line is that it minimizes the distances from observed variables, from observations to the regression line. And we said that we may consider using this kind of regression when x and y are an equal relationship, when y is not independent from x, or x is not independent from y. We said this regression line will be different from usual regression where you see y regressed on x, dependent y regressed on independent x, or dependent x regressed on independent y, and so on. These would be different regression lines that are minimizing different quantities. And I wouldn't say that one, let's say type 2 or major axis regression is better than ordinary least squares, let's say. It's not like that. It's just it's a different application. And we started by looking at this example of a paraglider moving in thermal and being sort of drifted in the wind. And when we were measuring the paraglider's latitude and longitude, we established that just regressing latitude on longitude or longitude on latitude doesn't make sense. There's some other hidden maybe factor, such as thermal, wind, and so on, which defines the position of a paraglider, and we're just observing latitude and longitude. So so these coordinates, in a way they're equal. It's not like one of them is defining the other. And in that case, we saw how major axis regression, right, seemed to fit the data very well. And we then saw the Excel example of how we could produce this sort of a graph. Now, before we wrap up sort of discussion theoretical part and then go into this fun exercise of actually fitting the complex movement of the paraglider, let's talk about this important subject. And the subject is that the model should fit the data generating process, DGP. So there's some sort of a movement, so there's something going on with this paraglider, right, on our example, where maybe paraglider is making circles in the air around some imaginary center, while this paraglider is being drifted or moved by the wind. So it's a complex movement, and how we were addressing it in the beginning with some sort of a regression of latitude on longitude, this linear regression, and obviously the movement of this paraglider is more complex than this, clearly, right? It's not like longitude defines latitude or anything like that. There's some other things going on. And yes, we were able to produce a reasonable fit using the orthogonal regression, but even orthogonal regression does not capture all the complexity of the movements of the paraglider. And I wanted to quickly share with you this little video. So let's look at this video of a paraglider or a bird moving in the air. And I grabbed this video from the paper to which I'm giving you the reference. I gave you the reference in, I believe, part 2 or part 1. So look at the spiral movement, right? So the bird or a paraglider is, at the moment, is probably soaring in the air upwards, I think. And there's some, it's a very complex movement. And oh, now it's sorting, right? So it's making circles. It probably caught the thermal, and thermal is lifting this object. Let's say it's a bird. I hope it's a bird, right? So again, another thermal, right? It's moving it up, and then there's a wind probably which is pushing the object to one side or another. So now let's just think of complexity of this movement, and how is it even possible that we would be able to catch it, to reflect it in our equation as this, or even if it's a principal component, even in principal component regression, it's still a linear relationship of this sort. Will we ever be able to capture something like what you're seeing on screen? Of course not, right? No. So what I'm coming to is the following: you can improve this model or truly reflect the underlying or truly understand the underlying phenomenon only if your model matches the phenomenon. And I'm saying model matches the DGP, data generating process. So there's this process of paraglider or a bird flying that generates latitudes and longitudes. Right, so that's your data generating process. So the original model and the PCA model both are, I would say, wrong in that sense that they do not match DGP. They're just they approximate with some sort of a um, linear regression of one kind or another. So how would you actually approach building a model that would actually um, reflect the DGP, data generating process? Well, you have to understand this complex movement which we're seeing on screen, right? So what's going on here? Maybe you would think that again, like I mentioned, the paraglider or a bird, they are circling around some center of their rotation, and then that center maybe we can capture with variables, latitude and longitude of a center, right? And then there would be some radius, so maybe that curvature of the circular movement is also changing with time. And then finally there would be some speed with which angular speed with which we are rotating, or the bird or paraglider is rotating around that center. And now this whole center is also being moved by the wind, right? And the thermal also move the center vertically. So maybe we could write some sort of an equation, maybe in state space type of setup, where we will have an equation for latitude and longitude, which are measurement equation, we will call it, because they are observable. We're observing only latitude and longitude. We are not observing the center, radius, or other things. Those would be the state variables, or hidden variables, latent variables, and so on. They have different names. So we will have then equations for state evolution. So maybe we'll take the center and then assume that it moves by some relationship, and we will try to estimate this equation too. And maybe for simplicity we can say the radius and angular speed are the same, but nothing prevents us from actually writing these equations down too. So we may end up with a bunch of coefficients in a complex setup like this, maybe in state space type of setup with Kalman filters, maybe if it's linear or non-linear Kalman filters, and so on. And maybe then we would be able to come up with a more realistic model which will capture the essence of the phenomenon. Now we spoke about ecology, I guess, in the part 1 and part 2 of this video. We had this extensive example of a paraglider, right, circling in a thermal. Now, what does this all have to do with finance? Do we have examples of such cases where we would be using, or we should be using, orthogonal regression? And I would say maybe or yes, there will be the cases. And let's look at this one example. I'm showing you the scatter plots of daily changes, daily log differences of VIX over daily log difference of S&P 500 index over, I think it's about 1 year data interval. And you could see there is clearly some relationship, I would say strong correlation, right? It's like an 80-90% range correlation. Now, so when you draw it like this, it's intuitively you sort of consume this sort of a graph as if changes in S&P 500 were defining the changes in VIX. And if you remember, VIX is sometimes called fear gauge, right? It's it represents at the money volatilities of options on SPX index 30 days from today, maturing in 30 days. Well, yeah, of course, VIX depends on what's going on with S&P, but you could argue that S&P also depends on options volatilities, right? So it's not obvious that VIX should be defined by S&P. It's not obvious that they should not be equal. And I could easily see the situation where I would say if not equal, then at least this relationship is not one way. It's not from SPX to VIX only. There is some leakage from VIX to SPX. If VIX is very high, it will cause SPX movements sort of jitter more, right? So there is some sort of a bi-directional relationship, and maybe in this case orthogonal regression would be appropriate, right? So and I could come up with some other examples of similar nature, but the point of this video was to introduce you to the usage of PCA and in particular type 2 or major axis regression, so that if you see the situation where it may be applicable, this tool will be available to you, right? And in part 4, sorry, of this video, we will look at now like more, how would I say, more complex implementation of the stance, which I said the model should match DGP, right? So we will try to create a model which matches data generating process, and we will produce a fit like this.